Okay, in the second part of our lesson 2.1, we're going to be talking about a few things that relate to some of the stuff that we've already talked about. One being using regression to model data points. Before we do that, though, I want to talk a little bit about this idea of correlation. Okay, when we have a scatter plot that we do, and whether it's whether it's in a line or a parabola shape or whatever shape it may be in, we can put what we call a correlation value on it. And when we're dealing with linear correlation specifically, okay, when we have points that are pretty close together and would be make a line between them look like a decent model, okay, we generally call that a strong linear correlation. And if they're moving up as we go from left to right, of course, we call that positive. Okay. Now, if they are a little weaker, if they're a little further spread apart, then we generally call it a weak positive. And if they're just in a big mess, basically we would call that little to no correlation at all. Okay. And of course we can do the same thing going negative. If we have points that are fairly linear going down as we go from left to right, we call it strong negative. And if they're kind of going down but pretty scattered, we call that weak. Now, one of the questions is there a scientific way to tell whether it's strong or weak, etc.? For the most part, it's a kind of a judgment call. Okay. There are some other statistical measures that we can do to actually make a calculation and decide whether it's strong or weak. Okay. Part of which is not going to be done in this class. I will show you, however, that there is a property that we call the correlation coefficient. Okay. And some of your calculators will actually give you the correlation coefficient, some will not. Okay. So therefore, we're not going to be held responsible for having to actually calculate it. But what it boils down to is the R value is between -1 and 1. If R is greater than 0, it's going to be a positive correlation. Less than 0, negative. And ultimately, the answer here to whether it's strong or weak comes from this. If the R value is approximately 1, okay, or very close to 1, so 0.99 something or 0.98 or something very close to 1, then we can say that that's strong. Okay, if it's closer to 0, then we'd say it's weak. So again, even this doesn't really give you a scientific way to decide, does it? Okay. It'd be nice if it said if it's greater than 0.7, then it's strong. If it's less than 0.7, it's weak. That'd be nice, but they don't tell us that. Okay. So like I said, it's pretty much a judgment call, even if you do know the R value. The bottom line is if it's close to 1, okay, then the answer is it's strong. If it's not close to 1, then we would say it's weak. Okay. In fact, if it was 0, we would say it's none. Okay. All right. So when you get that in your calculator, those of you who have it, that's what that number means. Okay. Now, getting back to what I talked about at the beginning here with this idea of regression analysis. Okay, we know that we've done this quite a bit already in this class. When we want to find an equation that models data, okay, we are going to put the data into our stat edit, if you will, or list, and then draw the scatter plot with the correct window. We'll find a regression model. If it looks like it's linear, we'll use linear regression. If it looks like it's quadratic, we'll use quadratic regression. Okay, and we also have regression, as I mentioned before, about some of the other functions that we know, like exponential regression, okay, logarithmic regression, okay, so on. And then, of course, we did this too. We superimpose the graph onto the scatter plot, okay, and then use the regression model to make predictions that are called for in the problem. Okay, this is kind of our general strategy in an outline form that we've been using. Okay, and like I said, we're going to continue to use this throughout this class. Okay, that's going to be kind of our model for any problem that involves data. Okay. All right, so what we're going to do now is we're going to look, in the first part of the chapter, we spent most of our time dealing with linear functions. Now we're going to look at some ideas with quadratic functions next. Okay. So the first question here is one that we know from what we did in lesson 1.6, which is how do we transform this into the graph of this? Well, let's start with the -2 part. If we put x minus 2 in there, okay, we know that that's going to give us a horizontal shift of 2 to the right. Okay. We know that this 2 out here, since it's outside the actual function part, is going to create a vertical stretch. Okay. And then the 3 is going to go take the whole thing and move it 3 up. Okay. So recognizing what's going to happen with that, okay, we can describe that in words, of course. Okay. So again, stretching the graph, we're translating it 2 to the right and also 3 units up. And so if we took that equation and did that, and one thing I wanted to cover at this point too is that when we have an equation like y equals x squared, and we look at an XY chart for it, if I do -2, -1, 0, 1, and 2, for my original graph of y equals x squared, I'd get 4, 1, 0, 1, and 4. And of course I could plot that parabola as we have been doing. Okay. One question I would ask is, do we have to, or could we make a chart for the new function, okay, based on just this part, okay, without actually having to plot those points? Well, let's think about what would happen here if I wanted to take the original point, starting with the -2, 4 point, okay, and if I were to move that 2 to the right, okay, what's that going to do to the x coordinate? If I'm at -2, what's that going to do to this coordinate? If I go 2 to the right, it's going to put me at what? 0. Okay, and if this is a vertical situation, then there's really nothing else that happens to the x. So that -2 would become a 0. What about the 4 though? Okay, if I do a vertical stretch on the 4, it's going to become 4 times 2, which is 8, and then 8 plus 3 would give me 11. Okay, so 0, 11 would be a point, and guess what? Look where my point is here, 0, what? 0, 11. That's that corresponding point, isn't it? Okay. Similarly, if I did it with the -1, if I move that 2 to the right, it'd be now at what? Which part? Right here? No, 0 for the x. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That'd be that point right there. So if we did the same thing with -1, if we move -1, 2 to the right, that's now going to be what? 1. And if I do 1 times 2 and then plus 3, it's going to be 1, 5. So let's check it out. 1, 2, 3, 4, 5. There it is. True. That would be that corresponding point. 0, 0, if I move that 2 to the right, that's going to be 2. And if I take 0 and I multiply by 2 and then add 3, I'm going to get 0, 3. Or, excuse me, 2, 3. So 2, 3, and notice that's the vertex, which corresponds to the vertex from the original then, doesn't it? Go ahead, Nash. And if I do 1, that's going to move over to 3. And then if I do 2 times 1 plus 3, that's going to be 5 again. So 3, 5 is a point, as we can see. And then finally, if I do that with 2, 4, the next point is going to be 4. And putting a 4 times 2, that's going to give me 11. And that's going to be that corresponding point right there, 4, 11. Okay. So again, without actually taking points and plugging them into the equation, just by knowing what we know about the transformations, can we make an XY chart for the new? Absolutely. Okay. If you think about what is that going to do, okay, to the original coordinates. Okay. All right. A couple features of the graphs of the quadratic functions that I want to look at. Find the slide that I'm after here. Oh, let's just start with this. Oh, that's the one I wanted anyway. All right. So we had one like this yesterday for a linear function, just some discussion about what the equations look like. So like we talked about yesterday, when we have a quadratic function, okay, we call this standard form when we write it like this. Okay, so this is standard form. Okay. Some books call it general form also, so we could write or general up here. All right, and then if I write it in this form, this is what we call vertex form. And if it's in vertex form, there's a couple of key issues here when we have it in either form. Okay, when it's in this form, it's convenient because the h and the k, okay, are the vertex. Okay, so vertex are h and k. So if it's given to you in that form, you can see what the vertex is right straight from the equation, which is nice. Okay, if it's not in standard form, okay, or if it's not in vertex form, I should say, then there's another formula right here, okay, that tells us how to find the vertex when it's in standard form. Okay, so if it's in standard form, the vertex is going to be found by doing this. And notice what we do. We do the opposite of b over 2a. Okay, and again, keeping in mind that a and b are just the coefficients on x and x squared. So if we do negative b over 2a, that's going to give us the x coordinate of the vertex. So I'm going to write that down here. This gives me the x coordinate of the vertex. Okay. So when we're in vertex form, we can see the vertex right from there. We don't need to do any work at all. Okay, but if we're in standard form, then we need to find the vertex by figuring out negative b divided by 2a and determine what that is. Okay. One other thing that's mentioned here too is one of the features of any parabola is that it's going to be symmetric. Okay. We know that the parent function is symmetric over the y-axis because the vertex is at 0, 0. Okay. If it is a parabola that's moved over, okay, then it's going to be symmetric over the line x equals h, and this x is going to be the x-coordinate of the vertex. Fair enough? So going back, let me flip back to the previous picture that we just got done working on, the graph that we did together. If you look at this one, the vertex is at 2, 3. True? So instead of being symmetric over the y-axis, it's symmetric over the line x equals what? Yeah, x equals 2. So that would be symmetric over the line x equals 2. So whatever the vertex is, whatever the x-coordinate of the vertex is, that's going to be also the equation for the axis of symmetry. Fair enough? Okay. All right. And then the other part I want to cover here as well is if I have a greater than or equal to 0, and notice that there's an a in this one and there's an a in this one. So whatever form it's in, we can see this right from the form. Okay, we can see it right from the equation. If a is greater than 0, then the parabola opens up. Okay. And if a is less than 0, then it opens down. So just by looking at the equation, we should know that it's an opening up or opening down parabola. Okay. Questions so far?
Is the k equals c minus h squared y?
Yep, I'm going to talk about that in just a second. Ultimately, again, we talked about this. If it's in standard form, we can find the x-coordinate of the vertex. Okay, the y-coordinate of the vertex, which is k for us. Okay, we can find the y-coordinate by doing c minus ah squared. Okay. Now, you can use this if you'd like to. Okay, but ultimately, if you knew the x-coordinate of the vertex, couldn't you just put it into the original equation and get the y-coordinate also? Okay, and that's ultimately what you're doing with this. They just put it in a kind of a nice formula form for you here, but ultimately that k is the y-coordinate of the vertex. Exactly. Good question. Question so far? Okay. C is the constant term. So a, b, and c are always the coefficients on the parabola. So to figure that out, you'll need c and a, and you'll also need that h, which is the x-coordinate of the vertex. Okay, let's take a look at a couple things here. A couple skills that we need to be able to do with quadratic equations today. The first one is we're going to take a standard form quadratic equation and put it in vertex form. Okay, so remember in vertex form, I would write out first, I'd write a times x minus h all squared plus k. I'd write out the general form first, and then recognize that I really only have to find three things. I need h, I need k, and I need a. Now, there's one thing that we already know. And what's that? Out of those three things I just mentioned, what do we already know based on this right here? I know a, it's 2. Okay. Now, what I don't know is the rest. I need an h and I need a k. So if I'm going to find the vertex here, okay, I'm going to need to use my formula that I just talked about, which is negative b over 2a. That gives me the x-coordinate of the vertex. So if I plug in my numbers here, I have negative 8. Make sure, especially if it's a negative b value, that you put it in parentheses so you don't mess up the signs at all. And then on the bottom, I'm going to have 2 times 2. Okay. And so ultimately, I'm going to have 8 over 4, which is 2. So the x-coordinate of the vertex is going to be 2 for us, so we can put minus 2 in there. We'll have that part handled. And then we just have one other part, which is figure out what is the y-coordinate of the vertex. And if you want to, let's go ahead and use that little formula they gave us, which is k. The y-coordinate is going to be, and they said, we'll look back at our previous formula. Formula, remember, was c minus ah squared. So if you write that down, c minus ah squared. So c for us would be, Jared? Boy. A is 2, and h squared is going to be 2 squared for us. So if we calculate 11 minus this whole thing, if we do the order of operations correctly, we'd square that and get 4. 4 times 2 would give us 8. And so the answer then would be what? 11 minus 8, which is 3. So that would be our answer. It's the same equation. If I were to put that in my calculator and put that in my calculator, we get the same graph. Okay, it's just in a different form. Okay, one's vertex form and one is standard form.